Hello everyone. Hello Siddhant.
I don't know.
Today it's the second part of Siddhant's interview, and in the previous video we talked about Siddhant education in India and how it happened that you came in Germany,
Yeah.
and we talk also about Bohmian mechanics. And today we will talk about your research topic, which is arrival times in quantum mechanics. And yes, you're working mostly on this topic. And yes, maybe I can say it again, even if I say it in the introduction of the first video, but you're assistant professor in Munich University.
I'm just a research assistant.
Okay, research assistant, sorry,
Yes.
in Munich. And yes, what should I add something or
No,
no?
that's
It's enough.
yet,
So
yet another physicist in the world.
yes, yes, you're a theoretical physicist.
Yeah, that's
And there are a few videos of you and your work on YouTube, but you your work has been mentioned at least 3 times, I think, by Tim Modlin in maybe 3 different podcasts. Am I right? Or
I don't have a count, but I'm sure they mentioned it a few times,
yes,
different podcasts.
yes. So maybe part of the audience already heard about you by Tim Modlin.
Yes, I think people who are usually following the podcasts
Yeah.
on quantum mechanics, where Tim is a frequent guest,
Yes.
they might have
Yes.
a bit about it.
And so last time we didn't talk about arrival times, or very briefly, but today and in the next video, or maybe next videos, I don't know how many we will do, but we'll be more specific, and we'll talk more thoroughly about arrival times. So today, I think the first thing we plan to do is to introduce you, I mean the audience, to the state of the art about arrival times in quantum mechanics. So you will explain to us what it means and why it's an issue for quantum mechanics. So I leave the floor to you. I let you speak, I mean.
Okay. So
You can share your screen or
yeah, sure. I mean, I thought before even I share and get into some notation and
yes.
physics talk, I could even say like I don't know if I mentioned it in the last interview we had. I'm sorry for the noise again.
No, it's okay. Yes.
Yeah, how did I come across this issue?
Yes.
And in my discussion with colleagues, I have noticed so many people are unaware of it as I was. And so a little bit about that, like it was a very surprise encounter. I mean, so as I was saying in the last podcast, I took a lecture with Detlef Duer, who is
Mm.
very well known in quantum foundations. It was a course on Introduction to Bohm's theory of Bohmian mechanics. And as I said, it was a very fast-paced course, and there was not really a lot of exploration of the Bohmian theory due to lack of time. But it was enough to kindle some interest in many of us. And of course, I met some of my very close friends in that lecture.
Okay.
But as I was just suggesting, the lecture it went further and gave me a lot of food for thought by the time it ended. But I was still thinking, is there I mean, of course, my first job was to engage more with the theory and see I mean, as I said, I became a big fan of the kind of explanations it provides for experiments. And my idea was a lot of my time should be about understanding just more about that. But towards the end of the course, Detlef invited the then PhD students of the group to basically give short talks about what they're doing. I guess, I mean, he was retiring soon, so I don't think it was an idea for him to somehow advertise the research problems that the group works on. I guess it was just, to give exposure to certain research topics that are not very common in physics departments, but are of deep significance in physics. And one of the talks was on arrival times, and I must say it was very different from the other topics because other topics really seemed plausible. I mean, you could see that the problems that are being solved are somewhat. I mean, it was quite clear that there's a technical problem here and people are trying. Now, when it came to arrival times, and I will explain more clearly what the issue is, the talk was by, I would like to take the name of my colleague, Nikolai Leopold. He was then finishing his PhD, I think. Now he's a postdoc, I probably in Trieste, but I'm not sure.
Okay.
Last time I spoke, I think he was in Trieste. So basically, and here I should just briefly mention about the arrival time problem and then give you a little more background. So, I mean, what I understood very clearly from the talk, I mean, Nicola is an extremely good speaker, was that the question that is being asked is, what's the time of flight or arrival time of a particle? So in quantum mechanics, as you know, there are various kinds of experiments which are done to, test various aspects of the theory. Each one of them is very surprising from a point of view of Newtonian physics. And we are engaging in many such experiments in a course in quantum mechanics. But a class of experiments that occupies a lot of space right from the beginning is a scattering experiment. That is an experiment where, you ideally send one particle at a time towards some obstacle. Obstacles are, like double slit or Stern-Gerlach magnets, and so on, or a potential barrier if you're interested in tunneling. So various kinds of electromagnetic environments, if you like, that you can expose your particle to. And of course, at the end of the day, you detect the particle, and it's very traditional. You use some scintillation screen, coupled to electron multipliers and so on. So that's an experiment every physicist has met in their training as a
It's very
physicist.
broad, I guess, because it could be several different kind of potentials, but it's not
Oh,
a free
yes.
propagation.
It could be free, for example.
Okay.
The simplest situation could be free propagation, but normally we are making it more interesting by putting various
Yes.
potentials.
Okay.
And even historically, scattering experiments have been a mainstay of quantum physics. That's the reason they occupy so much space in the early courses. But normally what one looks at in the scattering experiment is basically the distribution of the positions at which you have detection. So basically the impact positions. So you have a screen and you see these dots on the screen like double slit experiment. And what the theory is predominantly interested in and what's taught to the students is how to calculate the statistical distribution of these dots on the screen, if you like, or the impact positions.
So spatial distribution.
Exactly. So that's basically what we are interested in. Also, historically, the confirmation of the de Broglie hypothesis of matter waves was conclusively established in I guess it's the Davison-Germer experiment, which is cited as the the most conclusive one. I guess there were a few around that time, which is a scattering experiment where you have electrons being subject to a crystal, where the crystal lattice is like a potential. The nuclei deflect the electrons, and then you see like a wave-like pattern in the electron positions that you catch on the screen, that are caught on the screen. Of course, I mean, I mean, I wouldn't go too much now into the discussion of the scattering experiment, because I think now that I think about it, if one dwells a little more on what is the nature of this experiment and starts discussing it more physically in the lecture, if not all, I think some students will definitely ask about the arrival time question, which is, as I like to see it, and it's not disputed, that it's just another aspect of this kind of experiments. Just as there is a distribution in the positions at which the electron is detected, there is also a distribution in the times at which the electron is detected. It's also called the detection time for this reason. Now, in the experimental literature, this quantity, which is the time between, let's say, the firing of the particle and the final detection event finishing, it's called by various names. It's usually called time of flight. You can just call it arrival time from a classical physics perspective. We think of particles moving on trajectories and arriving. In any case, so the problem that Nikolai was discussing was the kind of challenges quantum theory faces in trying to answer this question in a satisfactory way. The question of the arrival time. So what is the distribution of the arrival time of a particle in a scattering experiment? Now, this should seem very surprising for anybody hearing it for the first time, because we were just mentioning that one aspect of the experiment, of the kind of experiment in which arrival time is measured, is very well understood and is even taught in introductory quantum mechanics courses. On the other hand, an aspect of the same experiment seems to have been the subject of extreme contention and debate. There is much more interest now. It was of interest. Covering the history can be tough in a very short span of time, but I think the number of papers that have been written on this subject has increased over time. What's really missing is experimental input. Of course, that is not to say that experiments haven't been done that measure arrival times. These experiments are in fact done very regularly. For example, CERN does it for measuring some other quantities that we can get into. So for many quantities of interest to the physicists, the arrival time is one of the first things that is measured. And then the measured arrival time is sort of converted into the quantity of interest. That should already raise some red flags, because we were just trying to suggest that the arrival time itself is not well defined or is contested. Like, what's the right notion in quantum physics? So now if I want to convert this, let's say for the sake of discussion, ill-defined quantity to something which is of interest, it's already tricky, right?
Okay. So there is a blatant asymmetry between the ability of quantum mechanics to predict position measurement outcomes and versus time measurement outcomes or arrival time.
I mean, prima facie, that's quite clear. I mean, you cannot write down a prescription for which physicists would broadly agree on for computing arrival times as they would for calculating the, let's say, the scattering statistics and position. So that's so I was sensitive to that already the very first time I got exposed. And it also occurred to me that it would be a very nice project for a master's thesis. I mean, I was considering a few other topics on the side, but it became clear soon enough that studying arrival time should be very nice.
Okay. And that's what you did.
Yes, yeah. And till today I'm at it. And yeah, it's a very productive thing to work on for
Mm,
young physicists.
mm,
And what I also like is from a certain practical point of view that it's it's arising in experiment. So the role of experiment is very strong in this kind
mm,
of research, which is
mm,
not the case in many other
mm.
areas of physics.
Yes,
And that makes it little, let's say, from a contemporary perspective, little safe.
yes,
In the end, at least you want to predict the experiments correctly.
yes. You
And
mean the debate can be settled experimentally?
yes, yeah, I
Yes,
think so, yeah.
yes. And also it's an issue for quantum mechanics, not just Bohmian mechanics or I don't know.
Yeah, I mean, of course, this is getting into the theory of it. Like once you acknowledge this issue and you get interested, you start asking, what are my options, right?
Mm,
Uh, if I mean, of course, in the end, you want to turn to a theory to come up with the predictions. I mean, then, of course, there is a lot of opportunity. You can be a complete phenomenologist, you can be a fundamentalist and knock various doors and see what you can do. We can get into that slowly. Um, well, as I was saying, so what's just good about all this is, in the end, all of these guys, no matter what are your starting points, everybody wants to get to the point where whatever they predict is confirmed by experiment.
yes. Mm,
Or confirmed within reasonable situation, right?
mm,
There could be some exceptional cases where the predictions don't work out, and those would be of more interest. But at least for the most experimentally accessible wave functions, because it's quantum mechanics, we are always interested talking about the wave function from the beginning. You would like to have a nice recipe which is at least as practical and simple enough, like you have
mm,
in the quantum mechanics textbooks, which gives you the correct answer for just about every simple situation you can conceive.
mm,
At least that's the hope. I mean, it could well turn out that that's not the case, but
mm,
we don't have any experimental indication at the moment that we have reached limits of theory and so on when it comes to arrival time,
okay,
right?
okay. So you want to start with the slides, maybe to explain, I
Yeah,
don't
so
know.
I can show you a few slides to explain a little more concretely how one
Yes,
set up this problem.
because I was about to ask you why is this problem, but uh, it will be in the slide, I guess.
I think I can I mean, if you're coming from a quantum mechanics course, let's say you
Mm,
have taken one or two courses in quantum mechanics, even at the graduate student level, um, the reason why it's a problem is rather easy to say in few words. I mean, if you want to predict the outcomes of any experiment in a quantum experiment, you are supposed to be talking about the observable that is
mhm,
going to describe this experiment in quantum mechanical language, right?
mm,
And if you go into the textbooks, you don't find any observable for the kind of experiments that we are talking about.
mm,
On the other hand, you have uh, prescription for how to do the scattering calculations and so on. Like in the double slit experiment, you can predict how the interference pattern looks like.
Mm.
It's at least discussed in the textbook. To what degree it is correct, we can of course we can go slowly, step by step into accuracy and so on,
Mm.
and how well things compare with experiment. But the simple answer why is it a problem is because from a standard QM perspective, which is in the textbooks, which is taught and forms part of regular practice, in that framework, the way to account for experiments is through what's called a quantum observable. If you like, it's normally a self-adjoint operator that you stick against the wave function and you get, according to very well laid out prescription, the statistics, the probabilities.
Mm.
That's not the case with arrival times. You don't have an observable which people sufficiently agree on that could be written down in the textbooks and handed down like the other observables.
Mm.
So yeah, that also starts the discussion in one direction that which many physicists in the literature uh, pursued, which is to basically figure it out. I mean, it could have been that for historical reasons, people just didn't care enough or didn't work out the needed observable. Um, but once you're cognizant of this issue, you might want to figure it out. And for a long time, it seems to have been the dominant program. The project was to find a suitable quantum observable which can give you the arrival time statistics.
Okay.
I mean, the reason it has been going on even now is, as you know, the observables that we use in quantum mechanics are sort of, I mean, the theory doesn't really tell you how to construct them. It gives you good motivation about perhaps why some of them look like the way they do, but
Mm.
let's be honest, they have just been figured out
Mm.
out of experience or good taste, and then they work and they have been confirmed in experiments and they're in use.
Mm.
But when you want to find a new observable, especially of especially one where you don't have much experimental guidance, it can be pretty challenging,
Mm.
right? So does that answer your question? Why is it
Yes,
a
yes,
problem?
yes, yes. Basically, it's because there is a lack of self-adjoint operator for time.
Yes, that's how it initially turned out.
Yes.
And
So
now there is also, the notion of observables has been generalized in recent decades, and people now allow what are called positive operator
yeah.
valued measures or POVMs to be also observables, just as the self-adjoint operators. I think there is a consensus in the literature that searching for self-adjoint operators for arrival time experiments is not going to pan out. Maybe there is still some room for it, but the kind of, uh, what should I say? It seems very limited, and people who work on it are quite aware of it. So the interest has certainly shifted into finding arrival time problems, which are generalized observables, if you like. Yeah,
Okay.
and every other day there is a new one.
Yes. Okay.
Okay, so how do we proceed? So should I try to give more, maybe a technical, slow introduction to the arrival time experiment and what people are basically trying to calculate or predict?
Yes. You mean with the slides?
Yeah, if you like, I
Yes.
can share a
Yes.
couple. Okay,
Yes.
right. So can you see my screen?
Yes. It's perfect.
So these slides are from a earlier talk that you have already watched.
No.
Um, Just a moment. I'll plug in the charger. So it's easy to introduce it as a single particle experiment where you have single particle wave functions involved. Not to say that it's limited to those. In general, you can imagine an arrival time experiment to be something where one or few particles are prepared at a source in some dependable quantum state, something that you can prepare again and again reliably. And you basically let the particle or particles move in space. And as I was suggesting before, you could imagine having various kinds of electromagnetic fields that the particles are subjected to. And the idea is, in the end, you catch the particles on a screen, and you could also imagine fancy screen geometries, um, and so on. And the experiment reports at the end of the day the time at which you see the click. So often the arrival time question can be phrased in a catchy way as when does the detector click, as opposed to where does the detector click.
And the issue is not to do this kind of experiment, it's to be able to predict the outcomes of this experiment, right? Or
The effort has been more on the theory side at the moment.
okay,
As far as experiments are concerned, there are arrival time experiments. As I
okay,
was suggesting, like CERN does it, and I usually maintain quite a list of these kind of experiments as and when I come across one. And they have been done for a long time. I mean, they're popular in quantum chemistry. Maybe I have a slide about that with a few examples of what kind of arrival time experiments are available and so on. But what normally happens is the experimenters who measure arrival times, kind of just use classical physics or Newtonian mechanics to interpret the data. They just imagine that the particle traveled on a straight line, if it was moving freely, and just use Newtonian mechanics to somehow, make sense of the arrival time. Like imagine if you drop an atom under gravity, even if you are sensitive to this arrival time problem, most people know that it's expected to be detected at the time at which the classical particle will fall, like the screen. So there is a lot of semi-classical heuristics.
yes,
So part of this project is also suffering from, let's say, the effectiveness of the semi-classical ideas, which are widely used in the experimental literature.
okay,
So,
because it,
so on the theory side, the first question is to predict something meaningful correctly,
yes,
and then also to somehow find regimes in which they will likely contradict the classical or semi-classical expectations,
okay,
which is when you can get experimenters very excited.
okay. Because so semi-classical treatments of arrival times work well, and
Yes.
so people rely on this I don't know models. And
Yeah.
okay, so and your job is to find a way to refute them.
Yeah. I mean, I think you can also see it as an opportunity. For example, if you see that some of these semi-classical Newtonian ideas work, and you are a theorist trying to propose a prediction for arrival time experiments, you might want to check that whatever you are suggesting is somehow compatible with what they are doing. Maybe you have a deeper explanation for why what they're doing is eventually effective, but you wouldn't, I mean, what I'm trying to say is if it so happens that in those regimes where what they're doing is in contradiction to what you are suggesting, then you are sort of in tension with the experiment. So there is, yeah, but so I think a short answer would be yes. We are interested in finding exactly those regimes that are amenable to present day experimental technology,
Mhm.
and which show something interesting, which show something, which is unexpected and, worth checking in the lab and so on.
Okay.
Right. So I guess I have gone through this slide. I mean,
Yes.
to sum up, just of course, you have to repeat the experiment, which is the last point I've written here. And
Yes.
you want to repeat the experiment under identical conditions, by which one normally means with the same initial wave function. So you
Yes.
prepare the particle again and again.
Okay, so you prepare your particles and you send it one by one, and you
Yes,
collect the data and you get your statistics.
exactly.
Mm.
And then you want to compare with the theory.
Mm. Yes, and the theory should give you a probability density.
Yes, so that's what's on my next slide.
Mm.
So given that you measure for all practical purposes random arrival times, the
Mm.
quantity you should be talking about is the density, the probability density, or the arrival time distribution. In the physics uh, literature, they're kind of interchangeably used.
Mhm.
And uh, for those who are not familiar, it's common to denote it with the Greek letter pi or p. And it's better to use a different symbol for the arrival time. Like I have tau here, you could call it t sub f. Normally you avoid t, or I recommend avoiding t, because normally the wave function changes with time. So you have a psi at every t,
Yes.
and you do not want to confuse the detected time,
Mm.
arrival time, with that t,
Yes. Okay.
which often happens. So
Okay.
it's better to choose different notation.
Mm.
Yeah, and as every probability distribution, it is subject to a certain kind of normalization, which I have put here in the box. This P infinity is something I can quickly explain. Normally, you would expect the probability density to be normalized, like in the sense that if you integrate it over all possible arrival times,
Mm.
it should give you one, right?
Mm.
Uh, but, and this is also very interesting, that it, as it happens that in some experimental runs, the particle wouldn't get detected.
Okay.
Uh, I mean, imagine an experiment. I mean, one common situation where that will not happen is, if you have the double slit experiment and you're sending one particle at a time through the slits. I mean, if the particle sort of reflects off from the barrier in which your slits are present, then this particle is not going through the slits and appearing on the other side.
Mm.
So even if you send, let's say, 10,000 particle, maybe 100 or
Mm.
200 of them make it through. So for these particles which did not get detected, you cannot define the arrival time because
Mm.
nothing was detected. So maybe you could say in theory the arrival time is infinity.
Okay.
So and there are other reasons why you would fail to detect particles. Like if your screen is not big enough, if it's a small screen, then many particles will not intercept the screen. And this is not something particular to arrival time experiments. This is just something that happens in any scattering experiment. Particles just get lost due to
Mm.
various obstacles and problems. So this P infinity is actually the fraction of non-detection events. So if you send 1,000 particles, 500 did not get detected, so it's half would be P infinity.
Yes. Okay.
Fraction.
Yes.
Yeah.
So if only half of the particles are detected, your integral must be equal to 0.5.
Yes, so basically you adopt a normalization convention in which the total integral of the arrival time distribution is equal to the fraction of detected particles.
Yes. Okay.
And sometimes it's you can also compare different proposals that are available in the theory literature on what they predict for this P infinity, because they actually come up with different predictions for that, and that's something you see in the experiment. So if
Okay.
yeah, so you can not only compare the predicted arrival time density, this P of tau, but you could also compare the non-detection probability, which is captured in this P infinity. It's a single number. It's just a fraction between 0 and 1,
Yes.
which is the ratio, basically the fraction of non-detection events.
Yes. Yes, it's just the probability for a particle not being detected.
Yes, yes. This
Okay.
is just one of the conventions according to which you could normalize.
Okay.
In any case, from a theoretical point of view, for a start, the arrival time problem calls for a prediction of this pi of tau or p of tau, given things like the initial wave function and the geometry of the detection surface, which is S here, as
Okay.
inputs. So I tell you what psi 0 is, what S is, and you're supposed to tell me what this distribution looks like.
Okay.
Yeah, I mean, of course, you can also say, what are the potentials at present? Like, did you put a barrier in between? Do you have magnetic fields? Do you have gravitational fields, and so on?
Mm.
Yeah.
Okay.
From a classical point of view, you have very similar situations. Supposing you were doing an arrival time experiment and you want to understand it from a Newtonian perspective, you would also specify what kind of forces are acting on the particle, what's the geometry of or the aperture of the detector on which your particles will be sensed. And as initial condition, you have to tell what's the distribution of the position, the momentum, everything that determines the motion for you. Yeah,
Okay.
right.
Okay, it's clear, yes.
So, yeah, so here I have, so this back then I was showing these pictures around quite a bit. And this also kind of gives a closure to our discussion about the scattering experiment, where you see the positions and also the arrival times.
Yes.
What you see in this picture is basically the interference pattern of a double slit experiment, which is familiar to everyone.
Yes. On the left.
On the left. So basically, what you see on the left is just like a picture of the screen after several particles have been collected, right?
Yes. For a double slit experiment.
For the double slit experiment, which is why you see the interference pattern. So this experiment was done with helium atoms. So
Okay.
it's quite an old one, actually, from 1996, 97.
Okay.
And what you see on the right is basically the arrival time or time of flight.
Yes.
They use the notation
TF.
TF to
Yes.
not confuse it again with the T. Um, so, for instance, if you imagine in the double slit experiment, once the particle is on the screen, it's a flat screen typically. So you have like two coordinates that you can assign to the dot that you see on the screen.
Yes.
At the same time, there is a time at which you saw the click. So of
Yes.
course, you need a very nice detector which can resolve the time of flight. And this experiment definitely had that. And they give you also the arrival times, the time of flight in the experiment. And on the right picture, you can see that the same detection events have been captured. The horizontal coordinate is the same.
Okay.
So they took one of the coordinates of the position of the particle on the screen at which it was detected, and they plotted it against the measured arrival time, as you can see.
Okay, so the particle's position on the screen is projected on one dimension, which is x.
Yeah, they just kept the X. If you like, you could have also shown it against Y.
Mm.
Yeah.
Okay, and so the goal, if I can say, of this slide is to show that there is an observable, there is
Yeah.
a property, even if we don't have a self-adjoint operator for arrival time.
Yeah.
So, okay, so we need to find something. I mean, by we, I mean
Yeah.
people working in quantum mechanics. Yes.
One has to find an acceptable way to deal with these
Ouais, yes.
quantities. Yeah.
We have to be able to predict these results.
Yeah, I mean, we are able to measure for sure. I mean, this
Mm,
is a very old experiment, of course, from a certain perspective. This is not the best experiment where you want to compare your theoretical ideas. But
mm,
double slit experiment is clearly the most iconic experiment. And in that, you can measure this arrival time. And here
mm,
is an example. Yeah.
mm. And the thing which I find striking is that we always, when we heard about the double slit experiment, we always talk about the position measurements of the particles on the final screen, on the screen, but we never talk about the arrival time.
Yeah.
And before talking to you, I haven't, I hadn't noticed it, but
Yeah. Same for me. I had never been told about it.
yes. But
And
once you notice it, it's striking and yes, it's disturbing in a way.
yeah, you immediately get the feeling that something has been missing
Yes,
in our description of this experiment.
yes.
And to be honest, if you even account for, if you become aware of the arrival time aspect of the experiment, you have to ask what is the path. So I mean the arrival time. So what I'm trying to say is in the left picture, which is of interest to us all the time,
Mm,
you somehow have to bring in the arrival time aspect because you see every dot on the left picture
mm,
corresponds to a different TF. That's what the
yes,
right picture is showing us.
yes.
It seems like in the ideal situation, to get the correct prediction for even the left picture, which is what we are always interested in, you might have to have you might have to make arrival time considerations.
You mean because particles arrived at different times
Yeah, because
on the screen?
so normally one is told that you should just try to calculate the wave function. First of all, already it is striking that people often use a stationary wave function, just time-independent Schrödinger equation,
Yes.
to account for the interference pattern, which already sounds a little strange. But even if you had a time-dependent treatment, one is normally told that you just square the wave function,
Yes.
which often gives you the interference pattern. You read off the maximas and minimas, and we are happy. But the problem is, when you square the wave function, which is evolving in time, the question is, at what time should I take my psi? Psi
Okay.
at which t should be squared?
Okay.
Because
Okay.
the data that you're talking about here, in principle, is not collected at a single t.
Yes.
After
Yes.
you throw the particle onto
One
the
by one.
slits, the detection time is always different in every run of the experiment.
Yes. 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 No. No. I get your point. Yes. Okay.
Yes, so that's,
Because you use your Born rule to get your probability density,
yeah,
but when you use the Born rule, you take the square of the wave function amplitude, but at what time?
yeah,
So you have to take the square amplitude of the wave function when it reaches or touches the screen. So you need the arrival time to compute it.
yeah. I mean, the time at which the wave, let's imagine you have a wave packet which is going
Yes.
through the slits. You have seen these pictures. Maybe there is one time at which the wave peak touches the screen or something, or maybe some
Mm.
significant feature of the wave crosses the screen, a simulation. But that's just a single instant of time. I mean, the arrival time, I mean, by which I mean the time at which you see the dot on the screen, may happen much in certain runs of the experiment. The dots could appear much before this instant of time. In certain other experimental runs, they could happen much later. As you see in the right picture, there's a whole range of TFs at which the data appear, like the
Yes.
particles are caught on the screen.
Mm.
So, for instance, if you want to predict the interference pattern, if you had access to the right picture, you would like to integrate out the TF. So you would add up all the TFs and then you would get
Yes.
some peaks and troughs which vary as a function of X,
Yes.
right? So, I mean, not trying to get too much into it. It can take us hours to discuss just the double slit experiment from a arrival time perspective. But you see that there is more to tell when it comes to this kind of standard experiment once you become sensitive to the arrival time question.
Yes. Yes.
Yeah.
Okay.
Uh, as I said, there is really no clear consensus. Of course, some ideas have become more popular, some have become less popular over time, but still, it's hard to say that there is a consensus on one particular way of doing it. And yeah, as back then when I was giving this talk, I really felt it's such a pressing issue that, the kind of theory that quantum mechanics is. And now we are talking about all its conceptual problems. There is so much interest in trying to discuss the foundations. But
Mm.
at least the theory has always been given a clean chit when it came to experimental adequacy.
Yes.
The framework of the theory, first of all, if you learn enough linear algebra and engage with the machinery of quantum mechanics, it's not a very complicated formalism. If you were to do an arrival time calculation in Newtonian mechanics, it actually would be probably much more complicated. You have to worry about the trajectories, which trajectories takes how long, and then you have to do statistics. Comparatively, if you have to just square a wave function with some approximate computations, the latter is much easier. So, what I'm trying to say is the empirical content of QM is very accessible after a point, and it's very successful. So it's quite, quite striking that we seem to have been in this situation when it comes to arrival time experiments.
Yes. It's not a conceptual issue.
It is quite a big issue, right? But yeah, I mean, yeah, so now for most part, we can only talk about theory because, as I just said in the outset, there is not much experimental data to discuss.
Mm.
I mean, data which is sensitive to, let's say, yeah, as I said, data where you really have to question the semi-classical reasoning and so on. Such kind
Yes.
of data is not available. So the discussion is just mostly theoretical.
Okay, so you will introduce us to the different theoretical approaches of arrival times.
Maybe a few. And as I
Yes, yes.
this is often gets very biased, as you know, because over time you have your favorites for reasons that one can also discuss. So many approaches get left out. Of course, if you at the moment there are about, I guess, 20 independent ideas, and if I cover each one of them, it's really,
Yes, it will be too
yeah,
long.
I'm not the best person for doing that. But I studied all of them, and
Okay.
so the year 2020 and 2021 mostly, I really spent weeks and sometimes a month on each of these approaches and doing very concrete calculations for all of them.
Okay.
So that was my last project with Detlef. As you know, he unfortunately passed away in
Mm.
January 2021. until then, we engaged in basically studying the consequences of different theoretical proposals for very specific experimental setups.
Okay.
So that is to say that I definitely could talk about all of the
Each one,
approaches.
yes. Yes.
I keep I think I'm quite updated even now. I continuously read and engage with the literature. But as I said, I also see, as any person, gaps and challenges that some approaches face and others don't. And I would like to spend my time studying ones that I find more promising.
Mm, obviously, yes.
Yeah. Okay.
Okay.
So let's see how deep you would like to go into this, because I don't know how much time.
I don't know. Uh,
Let's see. So maybe,
yes, we can. I don't know. Maybe we can
yeah,
give
let's
us.
let's start with one or two.
Yes.
Take a pause and see how,
Yes. Okay.
because then it becomes very technical, and I don't know if your aim is to have a very proper talk with a lot of details. But this slide is also interesting, if I may take a minute to
Yes.
just indulge you here and your audience. So, as I said, now the interest is quite evident if you go into Google Scholar and check arrival times and so on. And as I said, it was of interest before, but for the most part, physicists who took interest in this subject were often concluding that this stuff is not measurable and so on, which is a very strange thing to say if you mean by measurable something that the experimenter can report. But
Yes.
I mean, to be fair to these guys, what they're basically trying to say is either they could not find an observable, or they often try to include the physics of the detector, of course, in a very simplified way, which led to certain behavior that was not promising and so on. So you can see some of the quotations that I have collected here. This is a very small sample, I have to say. The general attitude, I think, has been, at least till 1960s even. The last quote is from 98. You can see people trying to say, oh, this is something, I mean, theory has somehow failed us here, so to speak. So this also has led to some, I mean, if you like, I can even explain a little more clearly why some of them are saying what they're saying here. At least I could say, for instance, this statement, which is sometimes
Uh,
called Pauli's theorem.
Good.
So
Siddhant,
what Pauli tried to do is he find a
Siddhant, the sound was very bad
yeah.
for 10 seconds or
Is
I
one
don't
of
know.
us stuck?
I think it's better now.
Yeah, let me just explain a bit more about Pauli, because his, or what came out of his considerations
Okay.
uh, did impact this area somewhat seriously.
Okay.
Basically, what Pauli was doing is he wanted to have an observable for time. I don't think he had in mind particularly arrival time or some other kind of quantity, but he just thought, quantum mechanics is all about observables. So why not have, and it was clear that time, to the extent it appears, is always as a parameter in the Schrödinger equation or in the Heisenberg equations of
Mm.
motion. So you talk about wave function at a time, or the Heisenberg operator at time t, and so on. So he somehow felt, I'm just paraphrasing to the extent I remember what he wrote. I read this long time back, I mean, a couple of years ago. He was basically trying to find a observable for time, which would somehow go along with the Hamiltonian, which is the energy observable, just as X and P go together. There's always the time, physicists are always talking about the time energy uncertainty relation. But everybody knows that it is not something which is as kosher as the position momentum uncertainty relation, because at least you have the observables for position and momentum, and you can derive this uncertainty inequality, mathematically speaking, rather clearly. But when it comes to the time energy uncertainty relation, the uncertainty in T has to be, at least given quantum mechanics, has to be defined with respect to a time operator, a time observable, which did not exist, and it still doesn't in the sense of having been, gained widespread acceptance. So Pauli is trying to formulate such a time observable, and he notices that if we demand that this time observable and the Hamiltonian commute in the manner the position and momentum operators commute, right? So basically, if you demand that this time operator commutator with the Hamiltonian is IH bar times the identity, which is something that will easily give you the uncertainty relation.
Yes.
He noticed that that would only be possible if the Hamiltonian has a spectrum that is not bounded from below.
Okay.
So self-adjoint time operator, self-adjoint Hamiltonian, which commute to give you the identity operator, implies that both these operators will actually have a spectrum which is from minus infinity to plus infinity.
Okay.
I think there are a few exceptions, like if the Hamiltonian has like only discrete eigenvalues like harmonic oscillator and all, maybe there is some scope. But in general, one does not expect the physical Hamiltonians to have spectrum going all the way to minus infinity, because one of the key ideas is the energy is sort of bounded from below, and like in an atom, which is understood to explain the stability of the atom commonly.
So it would
So
require to have negative energies and negative time.
yeah, for example.
Okay.
And then he said, that's crazy. So we have to abandon this idea. So that's where he more or less said the idea of a time observable has to be abandoned or something like that.
Okay.
My understanding is he says that even in a footnote, if I'm not mistaken.
Okay.
But that impacted the field for a long time. And many people were saying, I mean, they were more or less saying time is not observable and so on, which is correct in the sense of if you're, I mean, the word observable, it's a wrong name you give to a notion, and then it sort of confuses you. You have a feeling at this point, because from an experimental point of view, quantities like arrival times are as much, measured and reported as other
Mm.
quantities for which you have quantum observables, but you don't.
Mm. It depends what you call an observable. If you call an
Yeah,
observable a self-adjoint operator, so
then yes,
there
it
is
is
no
not
time.
observable. Yeah.
Yes, but as you pointed out in the previous slide, we can measure time arrival time. Sorry, so
Yeah.
it's an observable in this sense.
Yes.
Okay.
So I will not indulge too much on the history because I don't have the right slides, and if I
Okay.
try to do it too quickly, a lot of nuance might get lost, and I would like to be fair to everybody who made major contributions here. The guy Alcock who's mentioned here, he's certainly very well known in this field. He wrote 3 very long papers trying to seriously make sense of arrival times.
Okay.
Very long papers, and yeah, so at least he should be mentioned, I think. Okay, so I have already explained that arrival time measurements are very common in the experimental literature, and And I had mentioned CERN does these experiments and
It's used in spectroscopy.
yeah, it's used to what it's used in what's called momentum spectroscopy. You're just measuring momentum distribution.
Okay.
So, the idea is you would measure the time of flight of the particle
Mm.
and then just imagine that it was traveling on a Newtonian trajectory, which has a well-defined momentum. So at least for a free Newtonian particle, the momentum is not changing as it propagates.
Yes.
And you can reconstruct the momentum by just saying it's the distance traveled by the time of flight, right? Of course, times the mass. That's what they do. And the immediate question is, why are we allowed to do that? I mean, what's Newtonian mechanics doing here? If we are talking about particles going through double slits or if they're tunneling through barriers and so on, I thought Newtonian mechanics is inadequate for these experiments. So, yeah, so at the moment, for the most part, when it comes to theoretically treating the arrival times, it's Newtonian mechanics, 99% of the times, I would say.
Okay.
Um, yeah,
Okay.
so that's
Okay.
if
So
you want, we could
okay.
even go into some of these specific experimental techniques, but those would be probably for a later occasion. What do you think?
Yes, I think we can keep it for later.
Yeah.
We should just emphasize the fact, if I correctly understood you, that it's widely used.
Yeah. I mean,
Yes.
all the way from condensed matter physics to chemistry to
Yes.
particle physics, atomic physics, time of flight is a very important quantity.
Yes. So there
Mhm.
is a blatant contrast between this slide and the
Theory and
previous one.
experiment. Yeah.
Yes, and the quote of Pauli,
Yes.
especially. Okay.
If you take it too seriously, then there's something wrong here.
Okay. No, it's very clear.
One
Okay.
thing to say is experimenters should be a bit careful here because now the technology on the single atom, single ion level is so good that you can cool the particles and literally observe the spreading of the wave function as they evolve in various environments. And exactly in these regimes where quantum mechanics is supposed to show its most, interesting aspects. As an
Yes.
experimenter, I'll be very careful to just, be completely ignorant and just use Newtonian mechanics and think, oh, that's how it's done.
Mm.
And the hope is in the near future, theory guys who are working on this problem uh, can sort of point out certain regimes which are accessible to experiment today where we can really see the failure of classical reasoning.
Yes. Okay.
Okay, so this word cornucopia is from Detlef. He really liked to, it's supposed to be a fruit basket. So it's a funny way of referring to this proliferation of so many arrival time predictions.
Okay.
Um, at the time I was giving this talk, it's not too long ago, actually, maybe at most 2 years ago, I think. Um, one thing to note was there are so many of these proposals in the literature for, here is an arrival time prediction, there is another one.
Okay.
And many of them really did not work out the consequences of their theory or their proposal for realistic experimental situations. Part of the problem is the math is a bit harder. I mean, time-dependent QM in general, people know this, is difficult. That's why, for the most part, the textbooks are just doing time-independent physics and everything that you can do without having to find, let's say, a wave packet solution of Schrödinger equation or something. This experiment is not of that kind. So as it is set up, we are really interested in things changing in time, and so on. So the mathematical requirements are a bit demanding. So that explains in part why people haven't done it.
Okay.
But that's not enough. I mean, if you really want to knock on the doors of an experimenter and say, measure this and that, calculations have to be more than just plausibility arguments. I mean, you can begin like that, but really, one would have to do very serious calculations to take into account so many aspects. And I mean, I would hazard a guess that for most part, the approaches that we are talking about, they are really not capable of doing that. So they at best work for free motion without, let's say, time-dependent potentials and so on. Many wouldn't work for a magnetic field if you just switch on a magnetic field. And real experiments have everything there. I mean, to control the particle, for it to go from the source to the screen, you have to expose it to many controlling fields. And it could be that some of them really affect the final arrival time distribution. So if you want to test your prediction, you have to take into account all these things, and they just complicate the calculation so much that such calculations are not there in the literature. So that is a shortcoming of the theory literature, which I think will slowly get plugged. There is hope there.
So
I
slowly
mean,
get what?
it will slowly get plugged. So
Okay.
there is hope that, I mean, it's just a question of doing good calculations. I mean, we are bragging about having predicted magnetic moments to several decimal places. So sure, we can do these computations. Yeah, I'm surely pushing in those directions.
Okay. Okay. So the point is few of these theoretical proposals or get realistic predictions.
So few are capable of doing it.
Okay.
So that means that the others who are not capable, they already need sufficient generalization, if possible, to even be of interest.
Okay.
This question. So because of that, my efforts are mostly concentrated on looking at one or more approaches, which I think are really, from the beginning, they had the scope for making contact with actual experiments.
Yes. Not just simplified models or.
Yeah, yeah.
Mm. Okay.
But there are other workers, and they have, I'm sure, other priorities in this area.
Okay.
And all this also explains to some degree, as I have written here, why we don't have the contact between theory and experiment as it should be in this area.
Okay.
Yeah, because the actual calculations for realistic experiments are still slow in coming.
Okay.
There is this slide has to do with what I have somewhat indicated indirectly, that um, many approaches actually are compatible with this semi-classical um, ideas, let's put it that way.
Okay.
So there are, let's say, a couple of predictions which are quantum mechanical in the sense that they need the wave function and so on, like how we set up the problem, but they would somehow agree with each other in certain experimental regimes. Typically, they would even agree with the semi-classical calculation, which is based on Newtonian mechanics. So these kind of approaches are very difficult to distinguish if you are doing basically the obvious experiment, that is, throw the particle and catch it at a distance away, freely moving particle. So there is a consensus on this, that some approaches, not all, this is important, some approaches seem to just sort of look, I mean, they're hard to distinguish in let's say the regime where, let's say, double slit experiment is being done, where you're in the far field. So if our aim is to distinguish different approaches, we have to do a clever experiment.
Okay. But
So that's
it's
also one of the goals of
but
arrival times research.
technically it's harder to do to measure the arrival times in the near field.
Yeah, so I would say it's actually almost a no-no. I mean, the key problem is really if you place your detectors too close to the source, if that's what we mean by near field, typically
Yes.
what it means, then you just have a detection which is immediate. Like as soon as you fire the particle, you have a detection.
Mm.
The time between these two events, which is how experimentally you define the arrival time or transit time, it's a
Mm.
very small number. I mean, if your experiments cannot resolve, I don't know, nanoseconds or something, you wouldn't see a nice distribution. So indeed, it's very challenging that we cannot do the near field experiments, or we cannot I would say one should not recommend near field experiments for this reason. I mean, you could always say, oh, I want better experimental technology, and only then you can see the differences. Sure, I mean, that's a possibility. If you can bring in experimental equipment that can resolve very small, for all practical purposes, instantaneous arrival times, you have an advantage there. But the state of the art, more or less, is, I mean, you can resolve small arrival times, I would say. Maybe you have nanosecond accuracy. Some experiments even tell me they have picosecond accuracy. So one could capitalize on that, but it's not recommendable, I would say. And there is an understanding for that. People agree on this. And what's preferred is to have something where the wave packet spreads very, very much. So by the time detections are happening, you would expect like the width of the wave packet to be as large as possible. As you know, the wave packet spreads due to
Mm.
Schrödinger equation.
Yes.
And if the wave packet has a very wide width, you expect arrival times over a broad range. And these are very ideal circumstances for comparing theory, competing theory.
Okay.
Right. Yeah, we still haven't started talking about the different approaches. And this is a useful classification before we enter the zoo.
Yes.
You would find different options. And as I was just saying, so once you go into the theory and ask, how do I answer this question? So I don't have the observable. So one stream would be like, let's figure out the observable and what needs to be done to do that. And then there can be another stream which says, well, observables are just useful shorthands, and there is something deeper going on. So let me appeal to these deeper principles or theories to get the arrival time result. If in the end it can be summarized in the form of a self-adjoint operator, which is observable, so be it. But let me start deeper. That could be one idea.
Okay.
Another stream is you would say, oh, it's all about the measurement. So let me try to study the physics of the measurement device, which is ultimately responsible for reporting the arrival times. So if I explain the physics of that very cleanly, maybe I already know what the arrival times are. So there are different ideas that you could begin exploring. So broadly, there are like, if I mean, it's just a helpful classification. The boundaries need not be very rigid. So there are these ideal or intrinsic device independent arrival time distributions. That is basically those which don't care about what the detector does. Just
Mm.
like what we do in quantum mechanics all the time. Do you care about what's the physics, what's the coating on your screen, what molecules are present in your Stern-Gerlach apparatus? I mean, the experimenters surely worry about that, but for a theorist, when you're predicting it, you don't care. You are happy to be told that there is a detector at a certain distance away and so on.
Mm.
So the ideal device independent guys are in that uh, frame of mind, that they don't like to think, maybe it's fair to say that the physics of the detection is what we are seeing in the arrival time problem, right? I mean, they would think that we can define a device independent arrival time distribution and it will show up in the experiment. And to the extent that the detector makes a difference, could be some delays or some predictable perturbations or something. So that's the kind of idea in a
Okay.
physicist who is trying to approach it that way. So typically these approaches would often have a single particle wave function. Typically, like they wouldn't like to talk about the quantum mechanics of detectors and so on, writing down wave function for a huge system and so on.
Mm.
In contrast, the second camp is a bit like that. So they would really keep the physics of the detection process at the center of the discussion. And they have persuasive arguments for why that should be a good starting point. For instance, in the double slit experiment, if you monitor through which slit the particle goes, you know that the results change on the final screen. So there is a sense in which what you do matters, right? Very deeply. But at the same time, the first camp would say, look, we are talking about arrival times, like in a double slit experiment where we already have discussed the impact positions, the interference pattern. But we never talked about the detector there. So why should I suddenly take a very nuanced perspective on the detector in order to be able to predict the arrival times? Because my experience so far hasn't indicated any active role of the detector in these kind of experiments. So there is a lot of arguments in favor of either of them, and now the
Yes.
different approaches.
Yes. So if you accept the arguments of for non-ideal predictions, you accept to bring new requirements in predicting measurement outcomes in quantum mechanics.
You mean the textbook quantum mechanics?
Yes, I mean
Yeah.
usually your point is that usually we don't take into account we don't take it into account the measurement apparatus, or
Yeah.
in the sense that we don't model the interaction
The
between.
physics of the measurement device. Yeah.
Mm,
Yeah. So
okay.
if the non-ideal guys are supported in experiments, and if they end up in textbooks, sure, that would look very odd compared to everything else that's written in the textbooks, I would say. Yeah.
Okay.
But who knows? Time will tell. Okay. So
I was wondering because since I think we already did maybe 1 hour and 20 minutes.
yeah,
My,
I was also wondering if it's a good place to.
maybe we can just stop here today, and the next
Yeah,
time I don't know. What do you think?
I think it's a very good idea. I mean,
Yes. Okay. Okay. So let's do that, and the next time we will talk about
we
the
can talk
different.
about the different approaches
Yes. Yes.
and
It's probably
anything else.
better this way. So okay. So I stop the recording.